And this afternoon, last time we finished the first part of the script, which was about normal distribution, p-plots, visualization of measured data. And now I would like to go into the second chapter. The second chapter here, the second part of the script is about the quality control charts. It is a short chapter, and I think after that, we can start with the beginning of the next chapter, which is about probability and binomial and Poisson distribution. But at first, I would like to show you some sheets here and say something about quality control charts. You know a little bit about quality control charts from the QM2 lecture, where I've showed you some control charts, some examples for control charts in one of the TQM methods called SPC, Statistical Process Control. And quality control charts are a tool, a very important tool in SPC, in Statistical Process Control. And this is done, I think, in every industrial company for a monitoring and a documentation of the quality, of the production quality. So at first, quality control charts are a tool of SPC, and the goal is a monitoring of the quality by samples. So samples have taken out of the production maybe 5 parts or 3 parts. This is the sample size, which is usual. And usually you take 3 parts or 5 parts out of the production. You can do this every 2 hours or every 6 hours or one time a shift. There's no rule how often you take the samples out of the production. This is depending on the experience of the company. In most companies, they take 1 time a shift, a sample, or 2 times a shift. They take a sample of 3 or 5 parts out of the production, and then they measure some important quality characteristics, let's say some dimensions, and the mean and the standard deviation of every sample they write into the quality control chart. So over the time, over a week or over a month, they get a good impression of the level of the quality in this process. Every control chart is related to one quality characteristic. So this means one critical dimension or important thing like, don't know, strength or whatever the customer defines as an important quality characteristic. And in most of the cases, the customer defines which quality characteristics has to be documented and monitored in an SPC, quality control charts. So it is the monitoring of the quality by samples. With this, you get information of the quality level during the production. Also, you have a clear graphically presentation of the quality data over the time, and you can do long-term analysis and monitoring of the quality. It is a preventive method in comparison to final inspection of the parts. In the past, most of the companies made final inspection of the parts. But this has the big disadvantage that that a lot of parts are produced in the production, and then comes the final inspection, and then they see that a lot of parts are not requiring are not meeting the quality requirements, the tolerances, for example. And that's why they transferred the test not from the final inspection of the parts earlier in the production of the parts. So they see if the production process, if something is going wrong in the production process, they see it earlier, and they can react and can do corrective actions in the production process. So it is a preventive method to avoid much parts which are not meeting the requirement of the customer. So it's an early method of monitoring, controlling the production process. So the development is going from the final inspection, which was former times, to the process control, and this is what they do today in most of the companies. The goals are a low variation. This is one goal. Low variation means production precision. So they want to have products which have only very low differences and low variations from the other products. So the products in every process have to have a low variation, a high production, and precision. A high quality precision means a low variation. And also, of course, the centering of the process to the target value. The target value which you see in the drawing. Maybe in the product drawing, there is, for every dimension, you have a target value, and you have to center the process to get the target value, to get the process to the target value or nearby the target value. So control charts are a tool to detect systematic process disturbances. So if there is a, let's say, if there is a change of the machine, or if there is a change of the material batch, or you have other things, disturbance factors, and every disturbance of the process is detected by quality control charts. The detection also of scattering, also this means the scattering is the same as variation. Scattering means variation. To detect this, these control charts are a tool to detect if the variation or the scattering is caused systematically, like the change of the material or material batch, as I said before, or a change of the machine or whatever, or if the scattering, the variation is caused only by chance. It's only a random variation. The goal is to correct the process before scrap is produced. Scrap is waste. This is parts you cannot use because they are out of the tolerance. They are not meeting the customer's requirements, and so you can also you can rework these parts in some cases. In other cases, you have to put it into the waste because you cannot sell the scrap parts. And scrap parts are a loss, of course, because you cannot sell the parts. So this means you have to make sure in the production to have only very low number of scrap parts. The best is if you have no scrap parts, and the SPC with a quality control charge is to correct the process before scrap is generated or produced. And for that you have control limits, an upper control limit and a lower control limit. And these control limits are inside the tolerance area. We will see this in a few sheets later on. Well, what can you do with control charts? You can detect a drift of the mean by the time. You can detect the increasing of the variation. So if the variation is going bigger and bigger, you can see this on the control chart. And you can see if you reach the goal of a high process capability, this means a low variation. And process capability is calculated by the process capability factors, and here you have CP and CPK. If the process variation is high, then you have problems. The quality problems can occur and can cause special action at the customer or in the supplier company, like rework, or you have scrap. So you have special internal actions, or you have to go to the customer and do separating actions. You have to separate the good parts from the poor parts, and all these things cost a lot of money. And this is not the goal to do this. So it is the goal to get a low variation. And this means if you have only a low quality, this means big variations, you have automatically higher costs in the company. And this is a thing that cannot be the goal. Well, the tool is a quality control chart. And in the quality control chart, you have one line for the mean and one line for the variation. For the mean, you can use the median value of every sample. So you take out a sample, maybe 5 parts, you get a mean, and then here you get this mean of the sample, and this is what you write into the quality chart. As an alternative, another option is to write the median value of the sample, of every sample, into the quality control chart. And the third thing is a single value chart. This means you write every single measurement of every sample into the quality control chart. These are the 3 options. In most of the cases, the X-bar chart is used. So it's the arithmetic mean of every sample, and this is written into the quality control chart. And the second line is the variation line, and here you can write the standard deviation of every sample in it, or the range. Mostly they use the standard deviation. In most of the cases, they have an X-bar S chart. So the arithmetic mean is in the quality chart and the standard deviation. On the abscissa of the quality control chart, there is the time axis. And as I told you, there is no rule when to take a sample out of the production. You can do this every 2 hours. You can do this every 4 hours. Mostly they do it 1 time a shift or 2 times a shift. And then they take out the sample of, let's say, 3 parts or 5 parts. And then they do the measurements. Well, on the ordinate of the quality control chart, we have the quality characteristic. This is the measured value. So every control chart is only for one quality characteristic. This can be a dimension. This can be the weight of the part of the product. It can be a roughness, maybe a roughness in a sealing area. It can be the hardness, the strength, electrical resistance, and all other options which are important quality characteristics which are important for the customer. So the customer defines the quality characteristic of which has to be monitored and documented in the quality control chart. The control limits. You can define the control limits with a test run. You can define it if you have experience. The customer can define the limits, or you can calculate the control limits. In every case, the control limits has to be between, this means inside, the tolerance area. And this is an example for a control chart. Here on the abscissa, you have the timeline, the test time, maybe 10 o'clock, 12 o'clock, don't know, 15 o'clock, 20 o'clock, and so on. And here on the ordinate, you have the quality characteristic, let's say a dimension. Then here in the middle, you have the target dimension of the drawing. This is the target, which is in the drawing. And of course, it is the goal to reach this target in the production. And then you have the specification limits. These are the specification limits are in the drawing. Maybe let's say it is the quality characteristic is a dimension. Then you have the tolerance of the dimension in the drawing, in the product drawing. So the upper specification limit here, this is one tolerance limit, and here you have the lower specification limit, which is the lower tolerance limit. And now inside this tolerance area, you have the upper control limit and the lower control limit. And now every time a measurement is out of the control limits, this means above the upper control limit or below the lower control limit, every time this happens, the process has to be stopped and they must make a corrective action to bring the quality in this area between the control limits again. This means if they do this, they make sure that no part is going out of the specification limits. So they can sell every part. And this is the goal, of course. Every general director wants to sell every part. He don't want to have scrap. He wants to sell every part. And to make sure that every part can be sold, they must keep the quality between the specification limits. And for this, they have the control limits. This means every time when a measurement is outside of the control limit area, they have to stop the process, do corrective action to keep the process, to bring the process again here inside the control limits. Important are the equal times of tests, maybe every 2 hours, one time a shift, whatever. They have to define this. Equal sample sizes. So if mostly they take 3 parts, in some cases also they take 5 parts. The measurement equipment must be capable. They have to show the customer that the measurement capability, and the taking of the samples must be randomized. So every part must have the same chance to get into the sample. Well, this is the quality chart for quality characteristics with a tolerance. Not every quality characteristic has a tolerance. Some or most of the quality characteristics have a tolerance defined by the customer. And this is an example here for the quality control chart with a tolerance. This is a control chart for a quality characteristic without the tolerance. Maybe the weight of a part, maybe this is important for the supplier, but not important for the customer. In this case, the customer is not giving a tolerance for the weight of the part. And in this case, you have a warning limit, upper and lower warning limit, and you have also upper control limit and lower control limit. This means if a measurement is outside the warning limit area, so this means if it's above the upper limit or below the lower warning limit, then they let the process run, but they have to test more parts. Only if the measurement is outside the control limit area, then they have to stop the process and to make corrective actions. But if it's only outside the warning levels, in this case, they only make more tests. So the test frequency is increasing. They make more tests, but they let the process run. And a stop of the process is only if the control limit area, if a measurement is above the upper control limit or below the lower control limit. There are some other things you have to know if you work with a computer-aided system of quality computer-aided system like a CAQ system, computer-aided quality system. Then you have alert if you have a run or a trend. This means if there are at least seven measurements, this means 7 measurements or more on one side of the target value, then you have a run, and then you get an alert, which is an alarm signal from the computer, from the monitoring system, that there's something wrong with the process because this is not randomized. Maybe you have a systematic influence in the process. This means a run is if the 7 values or more values are above the target or below the target. This is a trend. Here you also get a alert or alarm of the computer. And a trend is if you have 7 measurements or more going down or going up. So if you have more than, if you have 7 measurements or more, which are going down, like here in the figure, or going up, then also it is a failure, it is a problem, and you get an alarm, an alert from the computer. And there is a third rule. This rule is called middle third. Middle third means 2/3, about 65–66% of all the measurements must be in a 1/3 area around the target. This means 1/3 of the tolerance. This is shown here. 1/3 of the target area, of the tolerance area, it's about 30% or 35% in this area of the tolerance area. If 60% or 70% are, so this means 2/3 of all the measurements are in a 1/3 area around the target, then it's okay. Here in this example on the right side, there are very much measurements. Many measurements are directly nearby the tolerances, and then you get also an alarm or alert from the computer because you don't meet the middle third rule. Too many measurements are directly here near the tolerance, and maybe here in this case the variation is too high. Maybe the process has a problem, and this causes the high variation. In general, if there is a value between the warning limit and the control limit, there is no corrective action. So they let the process run. If there are warning limits, so no tolerances. Only more samples has to be tested. This is what I told before in the sheet before. The statistical process control means products are coming out of the process. The process here is influenced by the 5M from, think of Ishikawa, 5M. And these 5M cause the reason for the product quality. Now they take samples out of the process, they get measurements of the samples, so they get information about the quality. And if the quality is okay, then everything is good, everything is fine. And if it's not okay, they have to perform corrective action in the process. They have to stop the process and do corrective action. The corrective action on the product, this can need rework of the product. In most of the cases, this is too expensive. They also have to separate the good parts from the poor parts, so the parts with quality and the parts without quality. So this is an additional effort, an additional action, and this costs money, and this is mostly not paid by the customer. So this is not a very good solution here. So the goal is, if there are some problems with the quality, and you see this in the quality control chart, and then you have, if there is a problem, you have to correct the process. The first step is to get the process get the process in a stable condition. This means the process is statistically capable. And here you see this process is not statistically capable because they have systematic differences from production to production. Maybe today they do a production and get a normal distribution like this. Next day, then overnight they stop the process. Next day they have the production like this. They have another mean value, they have another variation, another standard deviation, and maybe 1 week later they do another production, and then the mean value again is different, is another mean value and another standard deviation. So this is a process which is not under statistical control. So the first goal is to bring the process under control. This means that every production they do has nearly the same mean value. And then the next goal is to reduce the variation to get a smaller standard deviation. So this is the reduction of systematic variation and variation by chance. This is random variation, and this is the goal in every quality methods, and also of course in SPC. So there are two goals: process centering and an improvement of the process variation to get a low standard deviation, a high precision of the quality. Some of the quality characteristics cannot be measured directly after the production of the product. Let's look at this curve here. This is the shrinkage curve. So the dimension here is changing. The dimension is becoming smaller and smaller over the time. And here you see after 140 hours, you get the end dimension. And in the meantime, from the production until the 140 hours, the dimension is becoming smaller and smaller. This is a time-dependent shrinkage curve. And here it's very important that you measure the parts every time exactly after the same time after production. So let's say 2 hours after production, but not today 2 hours after production, and then we have the weekend, and the next time you measure after 30 hours or 40 hours. Then you are here in the time-dependent shrinkage curve before the measurement was taken here. And so you have variation problems in your quality chart, which are not caused by the process. They are caused by the time-dependent change of the measurement of the quality characteristic. In this case, it's a dimension. This can happen, this can be with plastic components, but there are a lot of other quality characteristics where you have a time-dependent delay. This means the end characteristic, the end measurement, is reached after a special time. What can be example for this? If you think of the cooling down of thick-walled steel parts, this can last hours or maybe more than a day. Which is, if these parts are reaching the room temperature, maybe they have a temperature of 1,500 degrees Celsius, and they are very thick, so it lasts hours or maybe more than a day until these parts are cooled down to room temperature, and you can measure dimensions or whatever other properties, other quality characteristics on the part after cooling down to room temperature. So the time from production to the end quality characteristic can be hours or even more than a day. Also, another example, the curing of varnishes. Varnish is a transparent paint, or paints, all these, or glue, of course. In all these treatments, you have a solvent, and the solvent evaporates. So it's going into the air. It evaporates. This means then it is not on the part any longer. It goes into the air. Evaporation is the word for that. And this you have with paints and with glues. Here's some examples. Painted surfaces. In every of these cases, every time you paint or you print a surface, you have an evaporating of the solvent. And you have to wait until the solvent is completely away. And then you can do a test. You can do tests of the adhesion of the print on the part, or of the paint on the part. So you have to wait a certain time after production and measurement. You have to wait until the solvent is evaporated. Other example, the burn-in of electronic components. You cannot test there are many electronic components. You cannot test them directly after soldering process, directly after the manufacturing process. You have to wait a burn-in phase. You have a burn-in phase of electronic components, and this burn-in phase can last several hours, in some cases a day or longer than a day. So only after this burn-in you can take measurements on the printed circuit boards here, or on the electronic components. This is a thing which burn-in is a thing which is used in many electronic applications. Also in mechanical systems, like in a motor for a car, you have also a test run. And you can also do pressure tests and other things here for the cylinder system. You can only do this after the first test run is finished. And the first test run means also about 2 hours or 4 hours or whatever of test run. The piston here is running in the cylinder over 2 hours or over 4 hours, and only after this first run you can measure the pressure, the compression here in the cylinder. So there are many examples where you have to wait a certain time until you can take the measurements of the quality characteristic. Okay, let's go back to the quality control charts. As I told you, the quality control charts, there every point here is usually not a single measurement, but is a mean, an arithmetic mean value of a sample of 3 parts or 5 parts. Now, it can be that the sample of 3 parts or 5 parts is not normally distributed. This can be, but the distribution of the arithmetic mean values in a quality control chart is normally distributed, even if the samples themselves are not normally distributed. This is one of the golden rules in quality management. This means if the sample size is more than 4 parts, more than 4 measurements. This means 5 measurements, 7 measurements. Then you can say the means are normally distributed here in the quality control charts. This sheet here is showing an example how to calculate the control limits for a control chart with a tolerance, with tolerances. This is for single value charts. So if you put every single measurement into the control chart, not the mean value, but every single measurement into the charts, and the sample size, every sample in the control chart is 5, n is 5, which is the sample size. Then you can calculate the control limits very easily. You take only the specification limit, and then minus T divided by AT is the tolerance. The upper specification limit minus the lower specification limit. This is the tolerance area here. And the lower control limit is the lower specification limit plus T divided by 8. So in many cases in the industry, they use this very simple equations here. If they have 5, n is 5, in many cases they use this also if it is n is 4, if it is n is 3. Then here you have some equations for calculating the upper control limit and the lower control limit. This is here for the single chart. Also, this means here for the single control chart, where every single measurement is in. Then you can take this equation to calculate the control limits. If you have a median chart, you take this equation, and if you have the arithmetic mean in the quality control chart, you take this equation here, these factors. In these equations, you see this estimated value of the standard deviation of the population, and this can be calculated with this simple equation here. It's 0.43 times the mean of the ranges. Every sample has a range, and if you have 20 samples on the quality control chart, you can calculate the mean of all the ranges, all the sample ranges, and then you can calculate this sigma roof value. You also can take this here, this dn is a table value. Mostly they do this, they take this equation here because it's more easy. And then it's easy to calculate the upper control limit and the lower control limit with these equations here. If you have a control chart without tolerance, so the customer gives no tolerance, there are no specification limits, and then the control limits are, you take the control limits for 99% data, in the 99% of the data must be inside of the control limits. And if you think of the warning limits, if you have no tolerance, you have warning limits, then 95% must be in the warning, inside the warning limits. You also, yeah, you can say the warning limits are the smaller area. It is the 95% area, and the control limits are the 99% area. So this means if you have a normal distribution here, you have here the warning limits, 95% of the distribution, and the control limits here for 99% of the distribution. If you don't have tolerances, you take also these equations here, like on the sheet before, and for quality characteristics without tolerance, you take these equations here for the control limits for x bar for the arithmetic mean. This is for the median, and this is here for the single value chart. This is for the median chart, and this is for the x bar chart. So it depends on the kind which quality chart you are using. Regarding the variation line, you can take the range or you can take the standard deviation. And here are the control limits for the R chart, for the range chart. You take the mean of the ranges of the quality control chart, and then you can calculate the upper and the lower control limit, and also the upper and the lower warning limit. This is for quality charts without tolerances. If you have tolerances, it's not so far away from these values. You see here, this is not a big difference between this 2.114 and 2.1, and here in this case it is 0 in comparison to 0.24. So there is not much difference if you calculate the control limits for quality cards without tolerances or with tolerances. And here you have some key terms or key words. What is a tolerance? The tolerance means upper specification limit minus lower specification limit. Here we have a limiting dimension. This is a dimension, can be a maximum or a minimum dimension, and this must be agreed by the customer. This cannot be defined by the supplier. It must be defined or agreed by the customer. The control limit, this is a limit to stop the process for corrective action, like I described it a few sheets before. A warning limit is a limit to increase the test frequency, but the production keeps running. This is only if there is no tolerance. A single value chart is a quality control chart with the original measurement value. A median chart is with the median values, and an X bar chart is with the arithmetic mean values. And this is for the variation line here. You can use the range for the variation plot, or you can use the standard deviation. Standard deviation here in this case is more popular than to use the range chart. In most cases, as I told you, they take the X bar S chart. Yes, here's an example. You have the measurements of every sample. This is the first sample, second sample, third sample, And here they have 9 samples, these 4, these 5. In total, they have 9 samples. And here you see when they had taken the samples out of the production, it was at 10:15. Next sample here was taken out at 10:25. So a lot of samples in a short time. Maybe this was a test run. Here at 10:32, at 10:45, and so on. So here you see the test times when they took the sample out of the production. And here you see the ranges of every sample. This quality characteristic is the inner diameter, and the inner diameter has a specification. This is the target, which is in the drawing, 12.7. And this is the tolerance also in the drawing, which is plus minus 0.05 millimeter. First, the tolerance is 2 times 0.05 millimeters. This means total tolerance is 0.1 millimeters. This is a tenth of a millimeter. This means the upper specification limit is 12.75 and the lower specification limit is 12.65. Sample size is 5, and there are, in this example, we have 9 samples. M is the number of the samples. N is every time is the sample size. Now you can calculate the upper control limit and the lower control limit by taking this measurement here, this equation, and you get an upper specification limit of 12.738 and the lower specification limit of 12.663. This is the tolerance, 0.1 here, tolerance T divided by 8, as I showed you a few sheets before. The sum of the ranges, if you take all these ranges here, in this example, all these sample ranges, and divide it by 9, then you get R bar. This is the middle, the mean of the ranges here. With these control limits, you can put these values, these table values, in the quality chart. And this is shown here. This is the quality chart. Here you see 12.70. This is the target. And then you have here, you have the upper specification limit, 12.75, and here the lower specification limit, 12.65, and here are the upper control limit and the lower control limit. And here you see the first sample, the measurements of the single measurement values of the first sample, here the second, the third, the fourth sample, and so on. And you see everything's okay until 11 o'clock, 11:05. Here everything was okay. Then you see the next measurement here at 11:55. It shows an increasing of the variation. The variation is bigger, but it is still inside the control limits. Then the next measurement is at 13:10. At 13:10, one of the measurements is outside of the upper control limit, so they have to stop the process and then to do a corrective action. After the corrective action, they do another measurement at 13:12, and then these measurements here are inside the control limits, which is good, but the variation is still too big. So they have to think about what can they do to reduce the variation. They will get a problem with the computer-aided quality system because here you don't have the middle third rule. If there are some others, some other samples like this further on, then the computer will give an alarm or alert, and they must do a reduction. They must think, what can we do to reduce the variation? Yeah, this is written here until 11.5. Everything was okay. Then at the test at 11.55, the variation was still okay, but it was larger, it was bigger. Then at 13.10, the variation was too large. There was a value above UCL, upper control limit. They have to analyze the cause for that and do corrective action in the process. Here another an additional example. If you take the measurements of the last exercise, of the last example, and transfer the data into a median range chart. So you can do a single chart, which we saw 2 sheets before. And now you also can analyze the data if you put these data, these measurements in a median range chart. Again, the tolerance is 0.1. Again, we have a sample size of 5 and 9 samples. And here the same values for the upper specification limit and the lower specification limit. With these values, we can calculate the mean of the ranges, which is shown here. And then we can also calculate the estimated variation of the population, which is called sigma roof. And with this, we can calculate the control limits for the median chart. Here the upper specification limit at 12, the result is 12.71, and here the lower specification limit, the result is 12.69. This is here for the variation line, and this is for the range chart for quality charts without tolerances. Here you can calculate this and you get these values. If you would take the equations for quality charts, range chart with tolerances, you would nearly get the same values. So here it's exactly the same value, and here you get 0 and here you get 0.0088. So it's nearly the same. So there's not much difference if you take the equations for a control chart without tolerances or with tolerances. If you put this in the quality control chart, you see here the median line. Here are the time, the points of time when a sample is taken out of production. Here you see the specification limits, upper specification limit, lower specification limit here. Inside here you have the control limit, upper and lower control limit. And what you see here is, if you calculate it with the equations, then you get control limits, and this can happen in many cases in practical applications. The calculated control limits are too narrow. They are too close together. So this range between these control limits is very, very small in comparison to the range of the tolerance. And this means you can calculate it, but if you have the problem that the range here of between the difference between upper and lower control limit is so small as you see it here, then it is better to take a practical value for practical reasons or from the experience to define a bigger range of the control limits. Let's say 12.73 to 12.67. This maybe is a much better solution than to take this very small calculated control limits. So it is better to use a little bit wider area here. And if you compare this area between these control limits, the red lines, with the specification limits, it is also very good, in a very good way between these specification limits. So why to use such a small area here, such a small area between the control limits? So it makes more sense to do a definition of the control limits by practical reasons, and in this case it is better to do it by practical reasons and to take not these calculated control limits. Here it is the variation line on the bottom of the control chart. You see the variation line, and here you see the range chart. These are the ranges of every sample here. And here you also have the upper control limit and the lower control limit. And you have the samples here, the sample ranges. Here's an example. The process for a precision molded plastic part, plastic component, should be analyzed in a pre-production by a single value chart. So we don't take the mean of the sample, we take every single value of the sample. For the analysis, 10 samples of the sample size of N is 5 were taken, and the process sensitive dimension was measured in millimeter. So here you see the 10 samples, and every sample has a sample size of N is 5. And here below every sample, you have the range of the sample. 10 samples, 10 ranges. You don't have a tolerance. And the job is to calculate the control limits and the warning limits, and then transfer the data into a control chart. At first, the mean value here is 9.5, and the sum of all the ranges, if you do an addition, the sum of all these ranges is 0.55. What can you do with this? You can divide 0.55 by 10. Then you have the mean of the ranges. Next step is to calculate the sigma roof, the estimated standard deviation of the population. This is this value here. With these two things, you can calculate upper and lower specification limits and upper and lower warning limits. Okay, if we do this here, this is the quality chart, and they didn't have much time. They draw this quality chart only by hand. And here you see the single measurements of every sample. Everything is running okay until this sample number 8, and then the next sample number 9 shows one value outside of the warning limit area. So they can let the process run, but they have to increase the measurements. Now they did different measurements. Again, these 10 samples with a sample size of 5. And then they put this into the control chart and they see it is running good until this point of time, until sample number 5. And then they have a trend going much too much in the direction of the upper specification limits. It is going through the warning limit and also through the control limit. So this means they have to stop the process. This is the control limit here, the upper control limit and the lower control limit. And here there are some measurements above the upper control limit. So they have to stop the process and to corrective action. What you can say here, what you can see here is a trend in the direction of the upper control limit. So they have to stop the production, control, correct the process, and check the new process condition. So they made several measurements again. These are 5 samples, again with sample size 5. And then they put it into the quality control chart. And now they see, okay, the trend is broken, but the variation is still too big. It's too large. And they have to think about what to do to reduce the variation. So this is a typical thing. If a new process is running and the process is not running after months, then they have solved all the problems. But this is an example here for doing it at the beginning of the serious production. Maybe it's a test run, and then this is a quality chart which is used during the test run of the process. Okay, this is what I wanted to show you about quality